In this video, we're going to introduce a new proof technique called mathematical induction. Induction is one of the most challenging or complicated proof techniques that we'll learn in this class, but also one of the most important, especially for applications in computer science. At its heart, what induction is a method for proving theorems of the following form for all n larger than or equal to some base case n naught, so this could be any constant, for all n greater than that constant, and what we're not saying here but almost always implying is that n is a natural number. So for any natural number greater than some base, some proposition p of n is true. So p of n might be, it could be any predicate. It could say that some function of n is even. It could be the statement that some equation describing n is always true, or some equation involving n is always true. So p of n can be any predicate. So the way that we do a proof by induction, this is very important. A proof by induction always has two parts. Always have two parts in a proof by induction. So what are these parts? The first part is called the base case. And what we do in the base case is we prove that P of n naught is true. So here we said, hey, this statement P of n, this is true for any n greater than or equal to n naught, so that includes n naught. So I should prove that P of n naught is equal to is true, and that's where I do one of my proofs. And here in this proof, I can do any proof technique that I've done previously. I can do direct proof, I can do proof by cases, I can do proof by contradiction. Then, and this is where induction can feel a little more challenging, I have a second step. This step is called the inductive step. And in the inductive step, what I do is I prove that for all possible choices of k greater than n naught, I need to prove an implication. I prove that for all choices of k greater than n naught, p of k implies p of k plus 1. So the idea of mathematical induction is that if I can prove both of these, if I can prove that p of n naught is true and prove that for any integer greater than k, if it's the case that p of k is true, then it's also the case that p of k plus 1 is true, then I've proven my theorem of the form for all n greater than n naught, p of n is true. So because this is an implication for all k greater than or equal to n naught, p of k implies p of k plus 1, I have a certain structure of a proof I need to do here. Often the inductive step is a direct proof. We just have to be careful about how we set it up. So we need to consider the fact that k must be greater than the threshold here. So we begin inductive proofs by saying, let k be greater than n naught, and assume that p of k is true. From here, I need to say what it means that p of k is true, and we'll look at an example shortly. This means that, and I need to fill in my definitions here, what it means for p of k to be true. Then I have some work to do, and then I'm going to conclude my inductive step by saying, therefore, p of k plus 1 is also true. That's where I got to get to. If I can do both of these proofs, I can do a proof of my base case and I can do a proof of my inductive step, then I have completed an inductive proof of the theorem that I'm trying to show. So let's take a look at kind of a visual representation of induction before we jump into some examples. Personally, I like to visualize induction as a ladder that I'm climbing. What does that mean? Suppose I want to prove a theorem of the kind that induction is suitable for. So for all n greater than n naught, some statement p of n is true. I'm going to prove it by induction. I have a base case. I have an inductive step. So when I visualize induction as a ladder, what I do is I visualize the first rung of the ladder, the one closest to the ground. That's the statement p of n naught. And what I do when I prove the base case, right here, is that I can get onto the ladder. I can take my very first step, and once I've taken that very first step, I've proven the base case. I am now on the ladder. Now, what my theorem says is that it's not just that p of n naught is true, but also every k larger than n naught also has p of k is true. So for example, here's p of k plus 1, p of k plus 2, and all the way upward to infinity. So each rung corresponds to a different mathematical statement, one for each possible value of k, and there's infinitely many of them because I'm talking about all possible n's that are larger than my base case. So what I want to do is I want to find an inductive way to prove all of these infinitely many statements. The idea of induction, specifically the idea of the inductive step, is to say, hey, not only can I, as shown in my base case, get onto the ladder, but every time, for every k, every time I can move from k to k plus 1. So in other words, not only can I get onto the ladder, but I can always take one step up the ladder. So this means no matter how large a k I'm looking at, no matter how large it is, I can always get there because it's always possible for me to get on the ladder and then climb one step at a time until I get to however high a value of k I want to reach. So this is the visual idea of induction. If I do two proofs, a proof of the base case and a proof of the inductive step, then I can actually prove infinitely many statements. I can prove infinitely many statements right here. For all possible choices of n greater than my base case, some statement is true. So that's the way that I visualize induction. And now that we've introduced induction and visualized induction, it's time to look at some examples.